Hello fellows, I am rummaging through my HP instrument collection and I put some items in suitcases. And as you can see, the suitcases have a NASA sticker on them. And the occasion is momentous. I am going to rejoin Carl and Ken and some others in Houston because we have been asked to help with the restoration of the Apollo guidance computer. For those that don't know, the Apollo guidance computer is this 1960 famed computer that was aboard the Apollo command module and the LEM and guided the spaceship all the way from Earth to landing on the moon. So you can imagine that when we were asked to help, we said yes pretty quickly and started to pack right away. Well, that looks promising. Ooh. Sorry guys, I have camera in hand.
Hi there, Mark, I'm Jimmie Loocke.
Must be Jimmy.
Nice to meet you.
I'm Tim.
Tim, nice to meet you. Hey Mike.
Hey.
Well, you have gloves, and here's the beast. Okay, we'll do the correct introduction later on. And I have the lights and all this stuff. Wow. No showy bow. This is the holy computer.
Glove on,
right? And pat it. No, I'll do that later. We should check if the analyzer made it alive. Hopefully.
Do you want me to open up the suitcase?
Sure. Probably do it off camera in case there's a big catastrophe.
SQ next. 365. A positive version of that. 302. SQ.
Which is our 370 input, right?
Right.
So it looks like I have just stepped into a hotel room full of nerds, my favorite kind of hotel rooms.
Do we have the SQ5 to take high on this?
And we all came here
Channel 3.
mostly because of this thing. So Mike,
Hi.
tell us what this is that I'm looking at.
So this is an Apollo guidance computer. This is one of the original 15 computers built. This particular one came out of the first man-rated lunar module, LTA-8.
Yeah, and by the way, Mike, sorry to interrupt, but
Yeah.
Mike is known because he has made an emulator of
Yeah.
the AGC, fully functional and gate exact.
Yep.
And now he gets to work on the real thing, because over here, going to turn to Jimmy. Jimmy over there. Hi, Jimmy.
Hi there.
Jimmy is the owner, and tell us a little bit about this computer of yours, where you worked at NASA, right?
I worked for a short time on the test of the Lunar Excursion Module, LTA-8. We actually man-rated the LEM for the first time. In other words, we simulated a mission to the moon where we actually had the astronauts in the spacecraft. In 1976, I walked into a warehouse looking for some electronic components, and I started seeing all this equipment that I recognized as being Apollo. So I wound up buying 2 tons of Apollo out of that warehouse, and my AGC was part of it.
So that was in the 2 ton. And you just told me at dinner that this was actually the AGC in the LEM that you were working on.
Yes.
The one that's and of course you were working in Houston. And you preserved all that, right? The 2 tons of it.
I had 2 tons of it, and for a long time I had no idea what I had. I knew that it was from NASA, I knew it was Apollo, but I was not really that familiar with some of the items, and it took quite a bit of research to figure out what these items were. I think it was 2004, I actually met with the lead designer of the AGC, Mr. Eldon Hall, and we opened it up for the first time and found out that it was unpotted, which makes it pretty unique. Normally your AGCs are potted. In other words, you won't really see much of anything except for these black modules. With my AGC being unpotted, you can see all the beautiful integrated circuits and the wiring and everything.
Here is one of the modules. Okay, before I go to the modules, maybe I go back to the picture of the AGC itself. So here it's 2 halves, and they're all made with this module. Maybe you can remove one.
Sure.
Maybe the memory or something that was easy to get.
Yeah, so we'll pull out one of these power supplies and just.
So these are the analog modules, right? So they,
yeah. So this is the 4-volt power supply.
Right.
It takes 28 volts in and puts 4 volts out.
So the nice thing is that it's all written on it.
Mm-hmm.
So for something that was made in a hurry, it certainly doesn't look like it was made in a hurry. Here, Cal's grabbing another one.
Careful there.
Trying to get it. So here's a more typical module.
Right.
Mm-hmm. So this is
Oh, that looks like a block 1 thing.
yeah. So this is a sense amplifier module. So there's
All right. Okay.
there's 16 sense amplifier chips in here. So it's frequently said that there was only one type of integrated circuit in the AGC, but there are actually 2. These sense amplifiers are another custom integrated circuit that they had made. So the red things down here are 2-to-1 transformers coming in from the core memories, and then the sense amplifiers pick that up, turn it into 1s and 0s.
And when Jimmie said they were unpotted, is that here is a... That's actually the module that this thing is famous for, because it has ICs in it.
Mm-hmm.
Right.
And we can see the ICs. Normally it would be filled up with foam.
Right.
Right, and we couldn't access it. But since this one was a development LEM, they didn't pot it, which means
Easy to test and repair. We
Right.
can get right in and check the signals on the chip.
exactly. So that was the explanation for the unpotted.
Well, he's getting a potted one out, right?
Yep.
Well, we have there are some that are potted.
Yep.
Just a
there's,
few.
There's the erasable memory, the current switch module, and the oscillator. So just to show
Oh,
what it
the
looks like.
erasable memory is potted.
Yes.
Core memory.
Oh. So if
Yes.
there is a fault in it,
Yes, there is.
and there is a fault in it, we are in trouble.
So
Looks black.
it is black. Yeah. We can't really see what's going on in here. So luckily, this is one of only a few in here that are potted.
Do we know if that one works?
Not yet.
Not yet.
Not
Okay.
yet. But this one only has magnetic cores and transistors in it.
Is it a read module for the memory, or
Yeah, so
for,
this
or
is-
driver for the memory?
Good drivers,
Yeah.
kind of thing.
Yeah.
Oh, cool. And we actually have the schematics of that thing. Can you show a few pages, Kyle?
So One of these pages is typically a single board. One of these modules has two boards, one on each side. So 2 pages of schematics, one of these slide-in modules.
And how did we get to find the schematics?
So Eldon Hall, the lead designer of the computer, had the schematics for all of the logic modules, and he made them available for scanning a bit over 10 years ago, I want to say, is when they became available. And then just more recently, Don Iles, who wrote almost all of the landing code for the lunar module, sent us a binder filled with schematics for all the logic modules and all of the rest of it, all the stuff that has been missing for the past 10 years.
So he sent you.
Yes, yes. So he mailed me this binder and I scanned it.
So the story is actually you wanted to build a replica that was exact,
Right.
and therefore you got to know everybody in it, and you were after the schematics, and eventually you found somebody that had it. That
Right.
was one of the original guys.
Yes.
And wow, that's a good find.
Yeah.
And so today we can follow the schematics and see if the gate work. Do they work?
So far, we have a 100% success rate with the 3 modules, with all of the gates, all of the chips in them. We did have one chip that malfunctioned initially, but we realized from the failure that it was probably a metal that was inside the chip, a manufacturing defect, and by shaking it, we dislodged it, and the chip works fine now.
So your repair was to shake it,
Was to shake it.
Yep.
and so therefore you can fly it again. It's safe.
This is not flight qualified anymore.
So actually, we found that some of these gates are flight qualified. Different modules have different sets of NOR gates in them.
Oh, and you can tell which one is
Yeah,
flight
the flight qualified ones have a red dot in the top left corner.
Means they were tested to that highest level.
Yeah.
Ah, wow, cool. And Mr. Ken has been hard at work also. I've been the only one goofing off and just filming things. Well, I just arrived, so I couldn't do anything else. What are you working on, Ken?
So these are core rope simulators that you can plug in place of the core rope, which we don't have, then connect to an external computer to simulate programs.
Explain core ropes. Core rope, right?
So to store the program for the Apollo guidance computer, it uses a special form of read-only memory called core rope, where they've wired wires through these cores to make the ones and the zeros. So the program is actually physically wired into this massive cores.
So that's what we would call ROM today. So that was the firmware, right?
So yes, that's the program in ROM. This was used for ground testing. So instead of core rope, they would use these core rope simulators that let you feed in a test program from an external computer. It would go through the simulator into the Apollo guidance computer, and you could run whatever you want.
So that box that you hold, that was in the AGC itself. It goes into the frame.
Right, so this plugs in instead of the core rope modules. So this is the same size as 3 of the core modules. Fortunately, we don't have any documentation for this, so I'm trying to figure it out.
Oh, that's not going to stop you.
It's not going too well.
Really? I can't imagine that.
So it has this cordwood construction.
Let me zoom on it. Yes.
It has this cordwood construction where they've mounted components vertically in a block of metal, so we can't see what they are or what they're doing. So it's very hard to know is it a capacitor in here, is it a transformer, is it a transistor? We just have to kind of guess and figure it out.
And we have no schematics for this thing?
Correct.
Great.
The other interesting thing is these modules here are used to hold integrated circuits. It's this bizarre technology that they used in the early 70s for prototyping integrated circuits that immediately fell out of favor, but we're still stuck with this. Plus the problem is that the metal inside these is corroding and falling apart into little bits. So we have all these little bits of metal that we're finding inside with the integrated circuits. So we have to pull out all these bits of metal before they short something out.
And they're metals from where?
Let me show you. So these are called dipsticks. Do you have the screwdriver?
Oh, they are part of a connector?
You would think so, but
And
Until you see what they are.
what's the second one? Is this another core rope module?
You have to use the two of them together.
Oh, okay.
Because there are 6 core rope modules, so 3 per box.
So let me open up one of the dipsticks and you can see what's going on.
You should ask that on camera.
I'm drinking from a fire hose here.
Wait until look at what's inside.
So inside the dipstick, they have 5 integrated circuits mounted on this little clip, and then you stick the clip into this matching clip, and the pins are pinched between these, and on the other side there's wire wrap pins where it's all connected. And there's supposed to be a metal bar that goes on top to hold these chips in place, but the metal bar has been falling apart into little bits of metal debris.
That's the one that's disintegrated.
And so you can see the metal bar stuck at the bottom here.
Ouch.
And because the metal bar is stuck, these 3 chips fell off the rail here.
There's chips. Alright, there you go, stuck at the bottom. So your core rope module emulator is probably not working at this point.
Well, it'll work. It just means the chips are stuck down there instead of up
they're
here.
still making contact.
But when you put it together, they will still make contact.
Alright.
Here you can see the underside of the dipstick, where each one of these is a pin of the IC on the inside, and then you can wire wrap your connections.
Well, that's not a bad. It's a clean prototyping technique.
Clean except for the metal debris and parts falling out and so forth.
Yeah, being picky.
And then on the top here they can put some decoupling capacitors.
Right. No, that makes for something that's prototype but very compact. So. And there, over to the side, we'll need a demo later on, but that's Carl's handiwork. You can you can recognize it right away.
Time pressure. Time pressure.
But this is a disky.
And a week to build it.
It's a disky built in a week. So obviously Carl was going for functionality because we absolutely wanted.
Keyboards.
We of course wanted, if we had the time, if we were able to hook it up to the AGC in the miraculous case where we can power it up.
It's designed for the 28-volt logic levels of the AGC, so all those boards around the outside are the interfaces that are exact matches to the impedance of the design of the AGC.
We expect no less from you, Carl.
Exactly.
So it's just this. So the that's what your red boards and green boards are doing.
Well, the green boards are doing it. The red boards, all the way to your left, are driving the 7-segment displays.
Oh, okay.
And then the boards to your right are controlling extra inputs and outputs, driving the sign bits, driving the warning lights, caution lights, and making the flashing of lights that have to flash.
It's ready to fly.
It's not flight rated.
Nice. What has your methodology been so far to test modules like these?
So the thing about these gates is if an input is open, it's low. So since these are NOR gates, the output will be high if there's nothing driving it. So
okay. Actually, by the way, that's a good point. It's only NOR gates.
Only NOR gates.
3 input NOR gates, right? They're all the same circuit in.
Well, they use some of them
right
as
there.
only 2 input, and they use some of them as just inverters, 1 input.
Right. But
physically 3.
It's made entirely of NOR gates,
Right.
mostly.
Yeah.
Okay, so sorry I interrupted.
So the methodology is because the rule is as long as both are low, the output will be high. Otherwise, you want to see each of the inputs being toggled and causing it to go low one by one to make sure that all the inputs drive the NOR gate on and off. So we want to see every NOR gate function with every input in each of its conditions.
Oh, you
Into
go
these
backwards.
rats.
So you look at
Exactly.
every output pins, and then
We go backwards to
Backwards.
say how can I force that high and low and isolate
Check the
it.
machine.
Every once in a while we have a thing that's too inbred to be able to isolate it. And then we'll use the voltmeter touching the pins on the chips to see the intermediate states. And as long as we can see every gate one way or the other operate correctly, we know it's good. It's laborious. This is a bit
So you are testing it
This is about 11
ga-
hours of work.
Gate by gate or group of gates?
Gate by gate.
They are 4,000 gates in that thing?
5,200 gates. So,
5,200, so I was...
yeah.
and you're going to check them gate by gate?
So 120 in
We've
this
been doing
module.
so far.
120 in this module. It's taken us about 10 hours. It's a very difficult module.
But like the scalar module went really fast.
Right. So
Well, because you can't tell if it works or not, basically, right?
they would just follow
So-
and make sure every output's working.
And actually, that's the one that didn't quite work, and you had to shake it.
Yeah.
Yeah.
This is what decodes opcode. So it basically
Right.
takes the opcode and decodes it and fires the rest of the CPU executing the instructions. So very important.
That's a control. Okay, well, good luck with that.